When an autonomous vehicle encounters a midnight downpour, the blinding glare from oncoming headlights can completely wash out its camera sensors. Traditional safety standards like ISO 26262 defined a vehicle as safe as long as the internal components didn't fail. In this rainstorm, however, nothing is actually broken. The hardware and software are functioning exactly as they were designed. To address this, engineers use a standard called SOTIF, or Safety of the Intended Functionality. It focuses on the unreasonable risks that occur when a system is defeated by the environment, rather than a mechanical malfunction. ISO 21448 Clause 12 serves as the final logical barrier in this process. It is the high-stakes evaluation a system must pass before it is permitted to drive on public roads. Ensuring safety in an open-world environment requires proof that the vehicle can manage these infinite environmental variables, even when every sensor and line of code is technically working perfectly. Safety examiners require more than just raw test data. They demand a structured, logical defense, known as a safety argument. Engineers use goal structuring notation, or GSN, to build this defense. This framework creates a transparent map where every piece of evidence, from sensor specs to track tests, links directly back to a core safety claim. This argument must first demonstrate completeness. The manufacturer has to prove they have identified all potential real-world triggers, such as specific weather patterns or road debris, that could cause the system to fail. Next is correctness. The examiner looks for proof that specific engineering changes, like adding a radar sensor to supplement the cameras, actually mitigate the risks discovered during testing. Finally, the argument must show consistency. This ensures the logical chain remains unbroken from the very first design requirement to the final validation results. These three attributes turn a collection of data into a credible argument, providing the evidence needed to justify a public release. Clause 12.3 subjects the developer's argument to an intense interrogation by asking 4 critical questions. Question 1 focuses on risk reduction. Engineers must demonstrate that their design changes have effectively lowered the dangers posed by known environmental limitations to a socially acceptable level. Question 2 addresses the minimal risk condition. If the system hits a performance limit, it must recognize its own failure and safely pull over or return control to a human driver. Question 3 evaluates coverage. Developers use statistical models to prove they have conducted enough testing to guarantee that the probability of encountering an unknown fatal risk is mathematically negligible. Question 4 looks at post-launch operations. The manufacturer must have a system in place to monitor the fleet and deploy software updates the moment a new, unforeseen hazard is identified in the field. Answering these 4 questions forces engineers to prioritize practical, real-world survival strategies over theoretical performance. Once the interrogation is over, Clause 12.4 issues a verdict: acceptance, rejection, or a strategic middle ground. This outcome is known as conditional acceptance. If a vehicle is safe in most scenarios but lacks data for others, it is restricted to a specific, constrained zone. This allows the technology to begin limited operations, such as driving only in clear weather, or gathers the remaining data needed for full approval. Conditional acceptance serves as a safety valve, allowing for technological progress while maintaining strict boundaries for public safety. Passing the SOTF assessment and entering the market is a milestone, but it does not end the manufacturer's safety obligations. The release argument stands as the definitive record that a manufacturer has fulfilled its legal and ethical duty to protect road users before deployment. This marks the transition into Clause 13, which governs ongoing real-world monitoring. The process becomes a continuous loop. As vehicles encounter new, previously unknown variables on the road, that data feeds directly back into the engineering process to refine the system's safety logic. This iterative process between real-world observation and engineering updates ensures the safety argument remains a living document throughout the vehicle's lifecycle.